All right, welcome to the holiday weekend. We're in the red here. That's bad, but okay, hovering around the green. That's not so bad. So, happy holidays for people in the United States. For people outside of the United States, don't worry about it. It's probably not a holiday where you are. Uh, it's a Memorial Day is the holiday. So I have off from work, so I'm going to spend that time to go through this book some more. All right, so last video we went through use case 4. Last video was kind of a unique video. It showed me working on perhaps submitting a contribution to the author, where I would push to his repo on GitHub and with a pull request. And what I would do is I would bring his simulator up to date so that it can run with the latest version of Pandas. The programmers of Pandas changed it so that it no longer has a method to append a data frame to another data frame simply by dot method. You have to use a different one. You have to use dot concat. So I thought it would be pretty easy to change that, but there were a few problems. So first of all, dot append, you can append a data frame to a dictionary, and you don't have to worry about converting the dictionary to a data frame beforehand. Dot cat, you can only append a data frame to a data frame, so you have to convert the dictionary first. And I tried that, and where it got tricky was there's one section in the code, there's one line in the code near the end, just one, where the author does a loop through a list, and they try to append something different from a dictionary, like an item in a list. It could be a dictionary still, but basically the author does something that I wasn't able to just simply stop using that dot append method and start using that dot concat. The code was just too far different between that old version that allowed for dot append and that new version that was dot concat. They weren't equivalent one-to-one methods that did the same thing, and there was something the author was doing in the code just in one instance in one place where that conversion I just couldn't figure out how to do correctly. So what I did is I scrapped everything. I just undid all my changes, threw it out, and I think this is kind of a good one because it shows like what you might do like in the real world as a software developer, that kind of thing where you go through, make some edits, test them, you think it through again, you go through, make the edits again, test them. You have kind of tedious work that you have to do that's just not fun. This really shows that. So if you want to really get a sense of what you might be doing some days as a professional software developer, even just a network engineer, because you're going to have to do that with like device configs, this is a great video to check out. So this is this is part 35 of this series. Really great video for kind of getting a glimpse into what you might actually do on the job as a software engineer. All right, but moving on, we're going to continue with use case 4, and we're on the problem resolution. One of the first tasks to do in any forecasting analysis is to understand our data. While we already know that our data has seasonality, trend, etc., we know it because we have explicitly generated it in this way. However, in a real scenario, you will simply get data from your router, switch, or cloud element. Visualization of it, like above, can give you an intuition of the seasonal aspect, but trends might not be obvious. We need a more analytical approach to extract those components from our data and understand its behavior better. There are multiple options. I have used the seasonal decompose method from the stats models SM library. Using the following routine, we get a clear decomposition of our data. So there we go. And we should get some graphs here. So I like to run it in my local because I have a nice GPU. If you're watching this and you want to run it, I definitely suggest doing what the author says and running it in Google Colab. Okay, so let's get back to the Jupyter Notebook. So Jupyter Notebook is down. So let's get rid of this dead port here, and then bring the Jupyter Notebook back up. Perfect. Open browser. Use case 4. All right, and then we're going to restart and clear the output. Oh, and look at this. So this is use case 4. I knew I was going to do this at some point. This is actually something that needs to get corrected right now. I forgot to change the path files to call upon use case 3. I'm surprised I didn't see an error with that yet, because I did call in some path files. So I don't know what the deal. I don't know why I didn't see errors with that until now. And so I selected a cell and I ran it out of order. So I ran this before df was defined. So let's start over. Okay, and defining that data frame will take quite a while. It took like 5 to 10 minutes the last time I did it. And I think part of the reason is because every single time we run that dot append, we get this message to say instead to use .concat. And I guess what I could do to make it go faster is reapply my changes where I made it dot concat instead of dot append, but then just get one single warning for the part in the code, which is it was near the end. It was line I think 18 something, but just that one part. Have that one part be the dot append method, and then I will get a warning just once rather than every single time. So that might be a good way to do it. This is why it's typically not a good idea to just blow away your changes that you made. You can stash them. You can put them in another file, or you could, saving. If you do a lot of work, you should probably save your work somewhere, just off in a stash in your local files, somewhere outside of the repo, in a stashed command. Git stash is meant for that. So definitely throwing out your work is never the best option. So that's one thing we could do is we've got 70 instances of this. We've actually got 86 instances of that. We could replace all instances except for, I'm surprised this is difficult to find. Oh, you know what? It's better to match on this. So yeah, 70 instances. We can place all instances except for this one here, where we can see it's a different kind of object. I think it's a list. Yeah, it's a list. And well, this is a index in a list, and then that object, whatever that is an indexable object, and we're going with the 0th index on that. So something about that object is different than all the other objects. That made it so that this one line didn't work. But as I said, if this takes 10 minutes to run because there's so many warnings for every line, and we don't know if it's taking forever because of the warnings, it could take the same amount of time. So let's just keep reading and make some progress in the reading, and then go back when that's finished. We can observe how a growing trend of about 2,000 over the period has been identified, pretty much linear. We can also see a clear seasonal pattern extracted that matches what we have used to generate it. And I need to sit down, so I will do that. There is a residual or noise component aligned with the fact that we are introducing anomalies in 4% of the data points. They are reasonably frequent over a sample that has 8,352 observations. There will be around 334 anomalies. A general practice to forecast properly when there is seasonality would be to extract the seasonal component. Then do the forecast with the trend as our new data and bring back the seasonal component at the end. I will not do that though. I will use the entire metric as is to evaluate how the algorithms behave given the entire complexity of the metric. When it comes to building a model for forecasting, you can forecast the next observation, or you can forecast one observation in the future, or you can forecast an entire period. Suppose you only forecast the next observation. If you end up requiring the forecast in a future time frame, you will need to run your forecast n times. This requires introducing the data you have plus the subsequent next forecasts computed until you get to the time of interest. The challenge of this approach is that with every forecast you are losing accuracy. It is forecast over forecast over forecast, and at some point the validity of the result is very questionable. In our case, I will take the approach of forecasting a block of values all at once. In particular, the goal is to forecast an entire day of data. Given data is sampled every 5 minutes, that means we need to forecast 288 observations. For that, I will use the data from an entire seasonal period, which is 1 week, 2016 observations total. The first algorithm we will use is a very simple one, usually referred to as the naive approach, which basically means the next observation is forecasted to be the same as the previous one. In a seasonal metric like this, the logic would be the next observation is forecasted to be the same as the equivalent on the previous seasonal period. Given our data frame, the prediction would look like this. All right, so there we go. So we get the prediction there. All right, so let's check into the notebook, and maybe we can get that far now. Nope, still working. So continuing on. Basically, I'm making the predicted vector y underscore pred underscore naive to be the metric values shifted by 1 week. That also means that we will not have predicted values for the first week, since we need 1 week of at least of data to be able to predict the next values. Therefore, our data frame contains NaN, not a number of values, for the first 216 values of the predicted values column. And we can see that there, so we'll have to address that. We just ran our first forecasting model. Doesn't it sound great? At this point, you may feel a bit disappointed. This is a simplistic model that is used as a baseline to compare other more sophisticated and adequate models. But still, in many cases, it may produce a good result because there is a strong autocorrelation of the data with its past values. We can estimate how good the model is performing by comparing the predicted value with the actual value of the metric at each point in time. We will use two metrics, the mean absolute error, MAE, which estimates the error based on the absolute difference. Sometimes the absolute error may not. What's the other metric we will use? Oh, okay, it's listed over there. So sometimes the absolute error may not be adequate, as it does not give a relative perspective based on the actual values. Alternatively, we have the mean absolute percentage error, MAPE, and the other metric is the mean absolute error, MAE, which normalizes it to the actual values, and therefore it gives more a sense of the degree or proportion of the deviations. There we go. We can plot the metric, black color, as well as the forecasted values for 1 day, red, and see how good or bad the alignment is. There we go. So one thing you could probably use this for, which would be pretty cool, is for personal finance. You can have it predict when you're going to have like a problem when you're spending, you're going to overspend, and then you can like plan an event for that time to try to change that behavior where you're like too busy to overspend in the way you would normally. We can see the alignment is reasonably good with two main issues. And sometimes overspending is due to a subscription that auto-renews, so it doesn't have to do with your behavior. But, this sort of stuff can be applied outside of network automation as well. I think it's important to understand these fundamentals as we head into the AI era. Which, I mean, I'm not doing. This is all going over my head, but I'm giving it a try. Since we are only copying the values from the previous seasonal period, week, we are also copying the anomalies. Therefore, our forecasted segment contains the anomalies of the previous period. While it is not very significant, we can see that the forecasted metric is below the actual metric in the target period. Since the metric has a trend, we simply copied the values. We are not capturing the expected baseline change over that period of 1 week, so the forecasted values will be necessarily lower than the actual values. Let's try another algorithm. This time it will be Holt-Winters. It is part of the family of autoregressive models, as we saw in the theory. It will use the past data, but with an exponential decay such that older data will have progressively lower influence on the forecast. We are using PLO. I think there's a typo here. I think it's meant to say exponential smoothing rather than exponential smoothing. But I'm gonna check that. I think well, you know what, ChatGPT is pretty good. So we're gonna start there, and then we're gonna go to Google. So we are using exponential smoothing function from the stats library. So we can see it right here. So this is from the stats library. So if it were PLO, it would have to be PLO down here as well, because that function has to be spelled the same. Otherwise, it wouldn't be called correctly. So we can see clearly it is a typo. There's no L meant to be here. It is the exponential exponential. Let's see, exponential smoothing function from the stats library. So I guess if you've got an accent or whatever, you might think it's exponential, but it's exponential. And let's get a pronunciation of that.
Exponential.
Yeah, exponential. It's even, you could misspell expen with an E here. Exponential.
Exponential.
Yeah, so the O kind of isn't, it's a mispronunciation. So that's an understandable error. It doesn't rise to the level of alerting the author. I have alerted the author of an error in the mathematical notation. That one is absolutely critical, because you could get the wrong idea that, oh, this has division in it, when no, it's a special character specific to probabilities. It has nothing to do with division. All right, so moving on here, we use the observations up until position 8,000 to train the model, and requesting to get a prediction for the next 3,000 observations, which corresponds to a bit more than 1 day. Also, we are letting the model know what is the seasonality identified, which in this case is 7 days, 2016 observations. If we run our performance measurements, we get the following results. There we go. Performance has improved with respect to the baseline, which is good. We can still observe a quite noisy prediction, likely derived from the fact that the anomalies are causing the model to also produce this variability in the forecast. All right, so we've got a graph there. Let's advance the bookmark and see if we can get up to that graph. So hopefully that data frame is built. It is, perfect. So we'll use the data frame. All right, and we're pulling this from the right path files path now, UC4 rather than UC3. So now we've got the data. So it's time to prepare the data. So see, we prepared the data by adding some columns to it. And now we've got the first graph that was shown there. Yep, so now we're printing out the that it's a data frame and then the contents of the data frame as well. Now we're defining a function and then calling the function. The function returns, the function prints out graphs. So we've got the graphs here. Yep. All right, so now we're on to the naive model. Okay, so we've got a data frame for the naive model with some not a number values. And let's see how this compared with the book. So the MAE for the model is about 13,000. The MAPE is close to 0. So quite a bit of a difference for the MAE. Theirs is much higher. Well, it depends on the magnitude, but theirs is quite a bit higher than mine. Theirs is 1780, while mine is 1297. So big difference there. The MAPE, again, it depends on the magnitude. It depends on the context, on the meaning of the numbers. But theirs was 0.22 where mine was 0.24. But again, there's a difference. Let's say that somebody is 2 inches taller than someone else. That's a smaller difference than if somebody was 1 foot taller than someone else. So the units matter a lot. It also makes a big difference. Let's say that there's a classroom and everyone's 5'2" tall. There's one person who's 5'1" and there's one person who's 5'3". So being the tallest person in that class, which would a percentage value, something like that would show that you were a standard deviation value would show that you really deviate from the standard. You are an outlier in the data, but you're only 5'3". In a classroom of people who are 4 foot, who are 7 foot, now if your average height, you might be taller than the outlier in that other classroom. So the context of the numbers makes a big difference. The units of the numbers makes a big difference. The type of the numbers, is it a percentage? Is it a magnitude? Is it a standard deviation? Makes a big difference. So it's really hard to tell how much different these numbers are. Depending on the magnitude, they could be very similar or they could be drastically different. All right, moving on to the next cell. And there we go. So, and now we're going to define the function, but we're not going to call it yet until this Wim Winters, or not Wim Winters, he's the guy that breathes. Yeah, let's move on. So let's try one method that we are already, Wim Winters is the piano guy. Wim Hof is the cold man. Let's try now one method that we are already familiar with, the Prophet library. We used in earlier use case Prophet. We used in a earlier use case, there's a typo there, but keep on going. Prophet for anomaly detection. We will use it now to forecast our BNG subscribers metric. The mechanism is the same. Instantiate the model with the data, in this case the first 8,000 observations, and then request a prediction for the future. Since we need to request Prophet to generate based on a certain frequency, in this case measured in minutes, we need to request a prediction of 1,500 observations. So 1,500 observations, not 15,000. Which corresponds to the 300 5-minute data points we are using as reference. So we're going to plot a graph here. Here's what the graph looks like. As we saw earlier, the profit model takes our metric into negative values when it tries to learn and model the seasonal components. It is very interesting how profit decomposes the signal in its trend and seasonal components, both weekly and daily. Particularly, the trend detected is extremely accurate. Let's run our performance benchmark and see how it behaves compared to our other models. Okay, so we're going to run the benchmark there and see what the difference is between theirs and mine. And it should be quite a bit different because I'm using my local and they're using the Google Colab. So, okay, so we've got here a value warning. No frequency information was provided. So inferred frequency 5T will be used. So that's just a warning. We can continue. All right, so it's going to take a while to get those benchmark numbers. They should be quite a bit different if this warning makes a difference. So all right, it's going to take a while to get those. So let's keep reading in the meantime. Results are actually better than with Holt-Winters. A visualization of the same data segment shows how the forecasted metric is not noisy as in the previous cases, but a smooth reconstruction of the signal where there are no anomalies. All right. So recurrent neural networks are also an option to do time series forecasting. Let's see how an LSTM-based network can perform to forecast our next 300 data points. We will set first a few variables that will be used when building our model structure and the different vectors. So here we go. There are the variables. Time steps, right here, 2016, refers to the length of the vector we will use to define our sequence for training. We want to use 2016 observations to predict the next 300 ones, next_predict. The intuition is that if we train the model with sequences that contain a complete week's worth of data, it should be able to learn how the next 300 data points should look like. Let's see if that hypothesis is good or not. First of all, it is very recommended to standardize our data and rescale it. Neural networks tend to work better when trained with values between -1 and 1. Large values will more likely saturate the activation functions, and usually that results in worse convergence during training. Scaling does not change the nature of the data, and we can scale it back to the original values because it is a linear function, so it will not change the results of our prediction. So here's our scaler. Now we need to generate our training data, effectively extract all those 1 week sequences, and generate our target labels, which are the 300 subsequent data points associated with each of the sequences we extract. This is what we accomplish in the following routine. Okay, so next we extract what part of our data will be used for training and which one for testing. All right, our data is ready. Now let's work on the LSTM model definition. Okay, this is how our model looks like. All right, you know what? Let me paste this in the ChatGPT, have it explain some things, and then from there, it looks like I messed that up. So change that, delete, close this, and try again. So, yep, so selected there. Looks good. So we'll paste this into ChatGPT, get an explanation, and then check back on the notebook. All right, ChatGPT is slow today. It's the holiday, so might be more people using it. And let's see if we can find the old chat. Well, you know what? I don't think I can. I thought it was called like linear regression something. No, it's buried. All right.
The image you provided illustrates a neural network architecture, possibly involving an LSTM, long short-term memory, network followed by a series of dense layers to produce an output vector. Here's a detailed breakdown of the architecture. Input matrix. The input matrix is of size n times 2016 times 1 n times 2016 times 1 n times 2016 times 1, where n is the number of observations and 2016 is the length of each observation vector. LSTM module. The input vector of size 1 times 20,161 times 20,161 times 2016 is fed into the LSTM network. The LSTM module appears to have 256 units, producing an output sequence with 256 features. LSTM output. The output of the LSTM module is a sequence of 256 features, each corresponding to an input vector of 2016 elements. Flanding. A sequence output from the LSTM module of size 1 times 2016 times 2561 times 2016 times 2561 times 2016 times 256 is flattened into a vector of size 2016. Dense layers. The flattened output is passed through several dense, fully connected layers. First dense layer, 1024 neurons. Second dense layer, 512 neurons. Third dense layer, 300 neurons. Output vector. The final output is a vector of 300 elements. This architecture suggests a model designed to process sequential data, like time series or text, using LSTM, followed by dense layers to transform the LSTM sequence output into a fixed size output vector. This structure is typical for tasks like sequence classification, regression, or other tasks where sequential data needs to be transformed into a fixed size output. If you have any specific questions or need further details about any part of this architecture, please let me know.
Alright, and I'm back. Sorry, sometimes I just do some other things while that's going. But I heard everything. It went all over my head. I didn't absorb anything, but let's check back in on the notebook. Okay, so we've got some results here. 1990.26. Okay, so now we'll run this. Okay, and I think the idea is that those will change. They'll get better depending on the algorithm you use. They're probably better than they were. The thing is, I don't know what these numbers mean. Tell me what these numbers mean.
The provided code snippet and the resulting output show the evaluation of a model's performance using two metrics, mean absolute error, may, and mean absolute percentage error, may. Code breakdown: mean absolute error, may, performance underscore hold point underscore may equals mean underscore absolute underscore error, df, y, 8000 to 8300, y underscore hold point underscore breadth. This line calculates the may between the actual values, df, y, 8000 to 8300, and the predicted values, y underscore hold point underscore breadth, for the model. May measures the average absolute differences between predicted and actual values. It is given in the same units as the target variable. Yep.
Okay, just tell me this. So, like, for each of these values, like, would it get more accurate if the value were larger or less accurate? Like, what does the number actually mean? Keep it brief and do not talk about anything besides the meaning of the numbers.
For both may and may,
perfect.
Smaller values indicate more accurate predictions. Larger values indicate less accurate predictions.
Okay, perfect. Okay, now act as an expert in this knowledge domain and expand upon the meaning of the numbers, but still keep it brief. Just do it with a higher level of expertise, please.
Certainly. Mean absolute error, may, definition. May is the average of the absolute differences between predicted values and actual values.
Okay.
Interpretation. A smaller may indicates more accurate predictions. It
Yeah.
quantifies the average magnitude of errors in the same units as the target variable, providing a direct measure of prediction accuracy.
All right.
Mean absolute percentage error, MAPE, definition. MAPE is the average of the absolute percentage differences between predicted values and actual values. Interpretation. A smaller MAPE indicates more accurate predictions. It expresses errors as a percentage of the actual values, making it useful for comparing prediction accuracy across different scales or units. Practical implications may have 1990.013. On average, the model's predictions are off by 1990.013 units from the actual values. This absolute error helps in understanding the typical deviation in the same scale as the data. MAPE of 26.26%. The model's predictions have an average error of 26.26% relative to the actual values. This percentage error helps in understanding the relative accuracy of the predictions, facilitating comparison across different contexts or datasets.
Okay, now create a tier list of some of the values that you might see.
Certainly. Here's a tier list categorizing different ranges of may and MAPE values, with respect to their implications for model accuracy. Mean absolute error, may, tier list, tier, excellent accuracy, may less than 100. Predictions are extremely close to the actual values, indicating highly accurate model performance. A tier, high accuracy, 100 is less than or equal to may less than 500. Predictions
these
are
are
very close to
pretty
the actual
bad.
values, indicating strong model
These are
performance.
C tier.
B tier, good accuracy,
Some of them are
500 is less than or
D-tier.
equal to may less than 1000. Predictions are reasonably close to the actual values, indicating good model performance. C tier, moderate accuracy, 1000 is less than or equal to may less than 2000. Predictions are moderately close
These
to the
are
actual
really
values,
bad.
indicating acceptable model performance. D tier, low accuracy, 2000 is less than or equal to may less than 5000. Predictions have significant deviations from actual values, indicating below average model performance. F tier, poor accuracy, may is greater than or equal to 5000. Predictions are far from the actual values, indicating poor model performance.
Damn.
Mean absolute percentage error, MAPE tier list tier, excellent accuracy, MAPE less than 1%. Predictions have very small percentage errors, indicating highly accurate model performance.
Okay, well that's good.
A
Getting
tier,
that.
high accuracy, 1% is less than or equal
Oh.
to MAPE less than 5%.
Wait, never mind.
Predictions have low percentage errors, indicating strong model performance. B tier, good accuracy, 5% is less than or equal to MAPE less than 10%. Predictions have moderate percentage errors, indicating good model performance. C tier, moderate accuracy, 10% is less than or equal to MAPE less than 20%. Predictions have noticeable percentage errors, indicating acceptable model performance. D tier, low accuracy, 20% is less than or equal to MAPE less than 50%. Predictions have high percentage errors, indicating below average model performance.
Oh, this
F
is
tier, poor accuracy, MAPE is
24%.
greater than or equal to 50%. Predictions have very high percentage errors, indicating poor model performance.
Yikes.
Contextual note: the specific thresholds for these tiers can vary depending on the application domain and the acceptable level of error for a given task. The above categories provide a general framework to interpret may and MAPE values in terms of model accuracy.
Okay, so this is good. So for this first one, we got for the MAE, we got let's see here. So 1297. So we got a C tier accuracy, but it's pretty solidly C tier. Pretty far away from that D tier. The book for this one, and remember we're doing a few of these to test the different kinds of models. So this is for the naive model. So this should probably be the worst one. And let's see where my bookmark is. So my bookmark should be here. So it's not advanced enough. So I'll advance it. All right, and now let's go back to the naive model and see what their accuracy was for that, and see how mine compares. We'll just see what tier the accuracy was in. All right, so here, this is what we're looking for. Is this? Okay, so for their naive model, they got for MAE they got 1356, which is C tier accuracy. What I got for that was for the naive model, I got 1297, so better accuracy than them, but still in the C tier. For MAPE, I got about 25%, which let's see here. Yeah, D tier accuracy, very, very inaccurate. They got pretty much the exact same I got. It looks like they were actually a little bit more accurate. I got 24.8, and they got so mine was more accurate still. That's cool. My local hardware is kicking. So yeah, they got but we're both in the same tier, so it kind of doesn't matter. We're both D tier, low accuracy. All right, so let's look at the next model, because the point is to see how the accuracy compares across models. So we used the naive model. Now we're going to use the Prophet model, PROPHET. Okay, so what they got for the Prophet model is 1959 for the MAE. So they got quite a bit worse MAE. In fact, they're very close to falling into that D tier, but they stayed just out of that D tier. So what I got for that is 1990. So I'm more solidly out of the D tier, but I actually got worse. Yeah, I got worse accuracy for that than they did, but we're both out of the D tier, thankfully. So, all right, and then the MAPE for this model, I got 26%. So That's a solid D tier, not so good. And they got 19%. So wow, okay, so they even made it up to the C tier for that. So my hardware really can't do this Holt Winters one very well, which is pretty fascinating. Theirs can actually do it better than mine. So this is good for ChatGPT. Okay, so I'm running a Jupyter notebook, and I'm running it locally on my hardware, and I have a pretty good GPU. I will tell you specifically what GPU I have. So the GPU I have is an NVIDIA GeForce RTX 2060. Yep. So that's the GPU I have. Now, the author recommends in this book to do these exercises on Google Colab because you get free access to their GPU and TPU that they have for free available. And I'm sure you can pay for more power, but the free tier is enough. So I'm just kind of I'm a tech guy, I'm a nerd, I want to do this my own way. So I'm doing it on my local hardware just to kind of see how they differ. And I am noticing a pretty big difference in what I am getting and, as compared to what the author is getting. Notably, we are using models. We are using AI models, and we are using algorithms. One of the algorithms we are using is Holt Winters, HOLTWINTERS. And we are testing the accuracies of the model. One of the way we are testing it is through MAE and MAPE. And one thing I noticed is that for the Holt Winters, the author's results are for the MAE 1780 and for the MAPE 21%. Now, my values are different for the Holt Winters. For my values, the MAE is 1990 and the MAPE is 26%. So what this means is that my values are worse. In fact, if we were to create a tier list, they would be in a different tier for the MAPE. But where it gets interesting is we also used another model. We used the naive model, and we got MAE and MAPE scores for that. My scores were about the same, but they were better for that model and worse for the other one. So what can this tell me about my GPU that might be interesting?
The differences in your May and MAPE values for the Holt Winters model compared to the values reported by the authors might not be directly related to the GPU performance.
Okay.
Here's a detailed breakdown of potential reasons and insights. Factors to consider: model initialization and hyperparameters. Holt Winters models are sensitive to initial parameters and hyperparameters. Differences in initialization or hyperparameter tuning can lead to variations in performance metrics like May and MAPE. Data preprocessing. Variations in data preprocessing steps, such as normalization, handling missing values, or data splits, can also lead to different results.
Yeah, so that could be it.
Ensure your data preprocessing step match those used by the authors. Software versions. Differences in software versions, Python, libraries like NumPy, Pandas, and staff models, can lead to discrepancies. Make sure you are using the same versions as the authors. Hardware differences. While your NVIDIA GeForce RTX 2060 is a powerful GPU, the dev model you are using, Holt Winters, is more CPU bound rather than GPU bound.
Okay. Yeah.
Therefore, the GPU's influence on performance metrics for this specific model is minimal. The naive model's performance consistency suggests that your hardware isn't introducing significant computational discrepancies. Insights on GPU performance. GPU utilization. For deep learning models, GPU utilization is crucial. Ensure your environment is set up to leverage the GPU effectively, e.g., CUDA installation, proper library configurations. Check if your deep learning models are utilizing the GPU properly by monitoring GPU usage during training. Comparing GPUs, global versus Google Colab. Google Colab provides different types of GPUs, e.g., Tesla K80, T4. While these may have different architectures and performance profiles compared to your RTX 2060, the differences in Holt Winters model performance are unlikely to be due to GPU differences. For deep learning tasks, the GPU type can affect training time and model performance due to differences in memory bandwidth, CUDA cores, and tensor core availability. Optimizing local environment. Ensure your local environment is optimized for GPU computations by keeping drivers, CUDA, and libraries up to date. Utilize tools like NVIDIA Insight or NVIDIA SMI to monitor and optimize GPU usage. Conclusion: the discrepancy in the Holt Winters model results between your local setup and the author's results is likely due to factors such as model initialization, hyperparameters, data preprocessing, or software versions rather than the GPU itself. However, for deep learning models, ensuring optimal GPU utilization and comparing performance on different hardware can provide insights into computational efficiency and model performance. To summarize, your hire may and may for the whole winners model suggests you need to verify inline hyperparameters and preprocessing steps with those used by the authors. For deep learning models, continue leveraging your GPU and monitor its utilization to ensure you're getting the best performance from your hardware.
Okay, so do you think this warning might have made a difference?
Yes, the warning about frequency information can indeed make a difference in your results. Here's why. Impact of frequency information on time series models frequency inference. The warning indicates that no explicit frequency information was provided for the time series data, so the library inferred a frequency of 5 minutes. If the inferred frequency does not match the actual frequency of your data, this can lead to incorrect modeling and predictions, affecting accuracy metrics like may and may. Seasonality and trend components. Hold winners models rely on accurate frequency information to model seasonality and trend components properly. Incorrect frequency inference can lead to improper seasonality adjustments and trend estimations, resulting in higher prediction errors. Addressing the warning to ensure accurate results, explicitly provide the frequency of your time series data when using the Hold winners model. Here's how you can do it. Check your data's frequency. Determine the actual frequency of your time series data. For example, if your data points are recorded every day, the frequency would be peak daily. Set frequency explicitly. When initializing the time series or using the Hold winners model, set the frequency explicitly. Here's an example. Conclusion: explicitly setting the correct frequency for your time series data is crucial for accurate modeling with Hold winners. The warning suggests that the inferred frequency might not align with your actual data, potentially leading to less accurate predictions. Correcting this by specifying the appropriate frequency should improve your may and may metrics, bringing your results closer to those reported by the others.
Okay, so we should have NVIDIA Insight Systems now. I don't see it. We do have the control panel. Okay, so that's not what we need. We need that Insight Systems. I just kind of blindly installed it without knowing without really paying attention. I do have GeForce experience, but that's just for optimizing games. That's not for monitoring it. And that's not one of the recommended tools. Yeah, NVIDIA SMI or NVIDIA Insight. We can open the file location here. There we go. And now we have a shortcut here. So now we can open it like this. Yep, there we go. So that's different from GeForce. Sure, whatever. Okay, so now we can yep, select that. And it'll prepare to select the target. There, and now we can see as we're working on this, we can see what the GPU is doing, how much it's task, how much it is being taxed, and more about the so yeah. Let's get the GPU metrics, and then yeah, and then we'll start. Oh, we have to select a process. I don't know how to do that. Okay, and this is just for games. You have to log into something. Yeah, you can't you can't do AI applications. Okay, so it says that it's ready. I'm not sure what I have to do. So I have to click this start button, but we can see the process name should be specified, and then the tracing graphs launched from device codes may significantly increase runtime overhead. So that could be a problem with that one that took like 5 minutes. If this just makes it take way too long, I won't be doing this anymore. But all right. So let's continue on with this. So what we're gonna do is maybe like that. Well, we have to select a process. So process name should be specified. So I guess let's look for the process. So it should be under C. It should be under NVIDIA. Display driver. International. Display.driver. Which okay, and let's talk to ChatGPT. ChatGPT is usually pretty helpful. So okay, so we're gonna feed it a few screenshots here. We're gonna feed it this one. Okay, then we're gonna feed it another screenshot. We're gonna feed it with this closed, just the whole thing. All right, the whole thing, and then okay, and then one final screenshot. We're gonna hit that start button, and then feed it the errors that show up. And then the question we're gonna ask it is, which process should be specified? Okay, so here's the question: which process should be specified?
To start profiling in NVIDIA Insight Systems, you need to specify the name of the process that you want to profile.
Oh.
This is the executable file of the application you're running. Here's what you need to do. Steps to specify the process name, identify the process.
Okay.
Determine the executable file of the application you want to profile.
Okay, I got
This
it.
can be your Python interpreter, python.x if you are running a Python script, or any other executable related to the application you are profiling. Set the process.
Okay, I think I get it. So if I'm doing things in a Jupyter notebook, I need to monitor that PYNB file. You know, the file that is used in the Jupyter notebook is the one I need to add as a process, right? Or is it like the kernel or something weird?
If you are running your code in a Jupyter notebook, the process you need to monitor is the Python kernel that is running the Jupyter notebook.
Oh, yeah.
Here's how you can set it up. Identifying the Jupyter notebook process, find the Python kernel process. Jupyter notebooks run on a Python kernel, and you need to profile this kernel.
I need to do that.
To find the specific process, you can use the command line or task manager to identify the running Python process.
Okay.
Using Insight Systems to monitor the Jupyter Notebook command line arguments for Jupyter Notebook, you will need to capture the command used to launch a Jupyter Notebook. This can be a bit tricky because the Jupyter Notebook starts multiple processes. Use psutil or similar to find process. You can use Python's psutil library to find the specific Jupyter Notebook process in the command line. Here's an example of how you might find the process ID, PID, of the Jupyter Notebook kernel. Profile the specific process. Once you have the PID of the Jupyter Notebook kernel, you can use this information to set up profiling in Insight Systems. Profiling with Insight Systems, specify the process name. In Insight Systems, you will need to enter the process name and PID you found using psutil. Command line example. The command line might look something like this. Steps to profile Jupyter Notebook kernel, open Insight Systems. Set target application. In the command line blue arguments field, input the command line for the Jupyter Notebook kernel. This will likely involve the ipkernel_launcher command. For example, replace lesson path _your_notebook kernel. JSON greater than with the actual path to your kernel JSON file. Set working directory. Set working directory to the directory where your notebook or kernel is running. Configure profiling options. Ensure the necessary profiling options are enabled, e.g., collect CUDA trace, collect GPU matrix. Start profiling. Click Start to begin profiling the Jupyter Notebook kernel process. By targeting the Python process running your Jupyter Notebook, you will be able to collect detailed profiling data on the execution of your code, including GPU utilization and...
Alright, so I need to monitor the kernel, not the file, because the file invokes the kernel, so the kernel is what I need to. Oh my god. Basically, when we go here and then we do kernel and we say restart and clear output, this is what I need to monitor, and it's not the same as this IPY NB file. We need to monitor instead a JSON file or whatever file it's meant to be. I think it's meant to be a JSON file because we can see here it's there. So yeah, we need this, and then we need to replace this with the actual path of the kernel JSON file. So we need to find where that kernel JSON file is. So let's feed it the screenshot of the logs from Jupyter. It gives you a running log when you run it.
Based on the screenshot you provided, it seems you are running Jupyter Notebook from within Visual Studio Code using the Windows subsystem for Linux, WSL. Here's how you can specify the process to profile in NVIDIA Insight Systems. Steps to identify and profile the Jupyter Notebook kernel process. Start Jupyter Notebook. You have already started Jupyter Notebook, which is running and serving in a specific port, e.g., http://127.0.0.1:8888/closing parenthesis. Identify the kernel process. Each notebook runs in a separate kernel process. You need to identify the specific kernel process to profile it. Using psutl to find the kernel process, run the following code snippet in a separate Python script or within the Jupyter Notebook to find the PID of the running kernel. This will help you identify the kernel process associated with your running notebook.
Found it.
Setting up Insight Systems. Open Insight Systems. Open NVIDIA Insight Systems on your machine. Set the target application. In the target application section, enter the command to start the Jupyter Notebook kernel process. Example command line. Replace less than kernel ID greater than with the actual kernel ID obtained from the previous step.
So process ID is 1738.
The PS of command output you provide lists the currently running processes, including the Jupyter Notebook server. However,
Yeah.
it does not show the individual kernel processes. To find the kernel process, you need a more detailed list of processes. Here's how to get a detailed list of processes and find the Jupyter Notebook kernel. Finding the Jupyter Notebook kernel process, run detailed PS command. Use the following command to get more details about the running processes, including the command line arguments. Identify the kernel process. Look for a process that includes IPKernel or the specific notebook game you are running. This process is the Jupyter Notebook kernel. Example command, run the following command in your terminal. This should show you the list of all Python processes, including those started by Jupyter Notebook. You need to find the one corresponding to your notebook. Profiling the kernel process. Once you have identified the correct process ID, PID, you can use it in Insight Systems. Open Insight Systems. Set the target application. In the target application section, specify the command line for the Jupyter kernel process. If the command to start your kernel is something like, replace less than kernel ID greater than with the actual kernel ID from your PSOF command. Configure profiling options. Ensure the necessary profiling options such as select CUDA.
Okay, so let's give it the more specific information.
Great, you have successfully listed the running Jupyter Notebook kernels. Each of these processes corresponds to a Jupyter Notebook kernel, indicated by the IPKernel_launcher command with a path to a JSON file.
Okay, which one do I need?
Example command to profile a specific kernel. To profile a specific Jupyter Notebook kernel using Insight Systems, you need to specify the command line that launches the kernel.
Okay.
For example, if you want to profile the kernel associated with the JSON file, home, gposh, global /share/jupyter/runtime/kernel-8.16-F438-49255-8A77-DD2D48.6217.json. Here's how you can set it up. Steps to profile in Insight Systems. Open Insight Systems. Set the target application. In the target application section, enter the command to start the Jupyter Notebook kernel process. Example command line. Set working directory. Set working directory to the directory where your kernel JSON file is located. Configure profiling options. Ensure the necessary profiling options such as collect CUDA trace and collect GPU metrics are enabled. Start profiling. Click Start to begin profiling the Jupyter Notebook kernel process. Example configuration command line with arguments. Working directory. Conclusion. By specifying the command line for the Jupyter kernel process, you can profile the performance of your Jupyter Notebook using NVIDIA Insight Systems. This setup allows you to collect detailed performance metrics and optimize your notebook's execution.
Oh, the executable is not found. Okay, we have to change the working directory to be the so it can be this. Shoot, but it has to be it has to target the WASL. Maybe this will work. No. This is such a nightmare. Do I have to use quotes here? Man, this is tricky. This is beyond me. Yeah. So the problem is, I think we're not targeting WASL. We're targeting Windows. Like we need this tool in WASL. We need to install it in Linux. So let's do that. So we've got yeah. So let's refresh this page to take us back to the beginning. And yeah, let's not install it for Windows. In fact, we can uninstall it. Let's uninstall it. Yeah, so let's go here. And then we'll close that, and then we'll go to okay, so we'll NVIDIA Insight. Yeah, so now we'll go to uninstall. So this is the control panel. We don't want to do that. we want to click here, uninstall. Yes, let's uninstall that. Because this is the Windows version, we're running this in Linux, so we need the Linux version. So, yep, .deb should be good. Oh, so this is to download it. Here's Jupyter Lab. Oh, perfect. This is exactly what we need. All right, perfect. So, yeah, we can even install it in the virtual environment. So this is what we need. Let's go here. Let's stop this. Okay, and now we need to do a pip install. There we go. And let's update our requirements.txt folder because we got a lot of like new things in here. So we're gonna do cat requirements. Oh, we don't even have a folder like that yet. That's fine. We don't need one. So now the real question is, how do we use it? Oh, so we have a video. Let's watch the video. Oh, NVIDIA Insight should show up at the top now once we launch this. So that's good. Jupyter Notebook, open in browser, and NVIDIA Insight should show up somewhere. Now, remember the last video I showed a video where a guy said he doesn't like using Jupyter Notebooks anymore in the browser. He prefers to use it in VS Code. It looks like that's how it's being used in the video, and I closed the video, so I got to open the video up again. There we go, and we can see they're in some strange. It looks like they're neither in the browser nor in Visual Studio Code. There's in some other kind of IDE. Yeah, they just have NVIDIA Insight listed there, where I do not. So, all right. So let's see if I can enable a widget. Okay, I don't know what that means. So let's see if we can download a widget. All right, that doesn't seem to be it. All right, so yeah, I'd love to do this to see what it's doing, but I feel like I'm just kind of wasting time here. Shoot. Yeah, I'm just kind of veered off course and wasting time. So, and now since I restarted my notebook, I have to, unfortunately, yeah. So they have a special NVIDIA Insight here next to Run, next to Kernel, next to Tabs. They're using a special tool here that I don't have access to. So really not a useful video at all. Now they might have ran a command. So this is a nsys command. Yeah, so they've got a special environment that I don't have, and they're doing things that I can't really do. All right, so let me get out of here one more time and then do. Yep, let's just make sure that's what I did. It is. So it's already installed. So man, how does this work? So we need this. Okay, so let's get that. Okay, and now that we have the prerequisite, I'll just run this again. I don't think I have to, but might as well. Okay, so now we enable it by using profiling / compute under the menu that we don't have. So let's try it again. Maybe that menu will pop up. So we have running, we have clusters, we have new here. Yeah, I don't have that. We have another in the IP and Y file. We have a different set of options. So we have file. But yeah, already I don't see that extra thing. I think we can't create a new notebook that has those. Yeah, we just don't have those insights. And that's too bad. Yeah, it just didn't work. I can't help but think it might be a widget, but we should go to the help menu. Let's go to notebook help. And then let's type in NVIDIA in a search if we have one. Okay, so we don't really have any useful help there, and we certainly can't search through it. All right, well, as I said, I'm just kind of wasting time on this. It's just not working the way. Let's see the command palette. Okay. No, so we don't have it at all. That's too bad. I wanted to see that. Nothing. Man, that's really too bad. I was excited about that. Yeah, I'm not seeing the front end expression, so we have to make sure that it's installed. Oh, is there? Okay, it's kind of weird because it's not. This isn't the command I ran. There was no dash. There was a space. So it's telling me a command I didn't run is okay, and it's even more weird. So okay, so it doesn't have lab extension. So maybe it just has extension. Yeah. So I think it's a different command now. Probably a different version. So Yeah, it's not enabled. So let's see if we can get a new extension. So is there like a install? Is there something like that? No, don't see it. Okay. So let's feed ChatGPT some more, see if we can get some answers.
It looks like you are considering using the Jupyter Lab NVIDIA Insight extension to profile your Jupyter Notebook cells using NVIDIA Insight tools. This is a great approach because it integrates Insight profiling directly into Jupyter Lab, making it easier to profile and analyze your code. Installation and setup. To install and set up the Jupyter Lab NVIDIA Insight extension, follow these steps. Install the extension, open a terminal and run the following command to install the extension. Check extension installation. Verify that the extension is installed and enabled by running. Using the extension. Once the extension is installed, you can use it to profile your notebook cells. Here's how. Enable Insight tool. In Jupyter Lab, use the command palette, Ctrl+Shift+C, and search for Profiling with Insight Systems Compute. Select this command to enable the Insight profiling tool. This operation may restart the Jupyter Lab kernel. Profile selected cells. To profile a specific cell, select the cell, then use the command palette to find and run and profile selected cells. Analyze profile session. The profiling information will be displayed in the cell output area. If you have the Insight Systems way enabled, you can open and analyze the report files directly within Jupyter Lab. Example commands. Command to enable profiling. Running and profiling a cell. Select the cell you want to profile. Use the command palette to run and profile selected cells. Troubleshooting. If you encounter issues with the extension, here are some steps to troubleshoot. Check extension status. Ensure both server and front-end extensions are installed and enabled. Reinstall or update extensions. If the extension is not working as expected, try reinstalling or updating it. Verify Insight tools installation. Ensure that the Insight Systems and Insight Compute tools are installed on your machine. Conclusion. Using the Jupyter Lab NVIDIA Insight extension allows you to seamlessly integrate NVIDIA Insight profiling tools into your Jupyter Lab environment. By following the installation and setup steps, you can start profiling your Jupyter Notebook cells and analyze the performance data to optimize your code. If you encounter any issues, refer to the troubleshooting steps to resolve them.
Okay.
The errors you're encountering suggest that while the Jupyter Lab NVIDIA Insight package is installed, there are issues with enabling and importing the extension in Jupyter Lab. Here are a few steps to troubleshoot and resolve these issues. 1. Verify installation. Ensure that Jupyter Lab NVIDIA Insight is correctly installed and check for any missing dependencies. 2. Check Jupyter Lab version. Make sure your Jupyter Lab version meets the requirements of the extension. The Jupyter Lab NVIDIA Insight extension requires Jupyter Lab 4.0.0 or later. 3. Rebuild Jupyter Lab extensions. Sometimes, rebuilding the Jupyter Lab extensions can resolve issues related to enabling extensions. 4. Manual installation of extension. Try manually enabling the extension using the following commands. 5. Check logs for detailed errors. Look for more detailed error messages in the Jupyter Lab server logs to identify any specific issues related to the extension. 6. Ensure correct Python environment. Make sure you are working in the correct Python environment where the extension is installed. Sometimes, issues arise from using different environments. 7. Verify permissions. Ensure that you have the necessary permissions to install and enable extensions. Running the commands with elevated privileges might help. 8. Clean Jupyter configuration as a last resort. You can try cleaning Jupyter Lab configuration and state. Example commands for checking and rebuilding. Conclusion. By following these steps, you should be able to troubleshoot and resolve the issues related to enabling and using the Jupyter Lab NVIDIA Insight extension in Jupyter Lab. If the problem persists, checking the detailed logs and ensuring that all dependencies are met will help in identifying the root cause.
Okay, yeah, not sure what's going on here. Now, there's no module found. I don't know if that means that I need to apt install rather than pipt install. Okay, yeah, you know what? Let's do it. Why not? So, but the thing is, okay.
From the provided screenshots, it appears that there are several issues related to the installation and enabling of the Jupyter Lab NVIDIA Insight extension. Here are some steps to resolve these issues. 1. Install Jupyter Lab. It seems that Jupyter Lab is not installed. You need to install JupyterLab to use the JupyterLab NVIDIA Insight extension. 2. Verify the installation after installing JupyterLab. Verify the installation. 3. Reinstall and enable the extension. Reinstall the JupyterLab NVIDIA Insight extension and ensure it is enabled. Enable the extension. 4. Rebuild JupyterLab. Rebuild the JupyterLab extensions. Example of correct installation and enabling. Here's a step-by-step command list to ensure everything is installed correctly. Troubleshooting. Check for errors. During each step, check for any errors in the output and rest them as needed. Python environment. Ensure that you are operating in the correct Python environment where all dependencies are installed. Permissions. If you encounter permission issues, try running the commands with elevated privileges, e.g., using sudo. Conclusion. By following these steps, you should be able to resolve the installation and enabling issues for the JupyterLab NVIDIA Insight extension. Installing JupyterLab first and then enabling the extension should help you integrate NVIDIA Insight tools for profiling your Jupyter Notebook cells. If the problem persists, please refer to the logs for specific error messages and address them accordingly.
Shoot. Okay, so we're still having a problem. Man, that's so weird because I have it. Do I need to do pip3 install? I mean, I have a virtual environment enabled. It's the same command. An out of memory error? That's not what happened. Man, this is a lot. And this is what as awesome as ChatGPT is, like, it can't do this. Like, it doesn't matter how powerful it is. It can't tell me, you know, like an expert in computer science, like Sam Altman and his team could tell me what's going wrong here, but ChatGPT cannot. Like, it's just not there yet. All right. Well, you know what? It's broken. It's never gonna fix. So we're gonna restart the kernel. We're gonna leave. Yeah. Close all this. Leave. Maybe it's because there's maybe it's because the port is still open. No, the port is closed. We got a problem here. Stationary is not defined. Oh. Okay, I don't know what's... Maybe I have a change there to... This is sans.py. No, I don't. What? Okay, well that's a big problem. Anyways, I'll just open Jupyter Notebook, and then we'll just pretend none of this happened. It'll be like the other video. We'll just keep this secret and never talk about it again. Okay, so yeah, man, it'd be so cool to be able to monitor that, but nope, it's just not in the cards. I'm not good enough. I never will be. All right, so it's now it's gonna take like 5 minutes to get there, but we can read in the meantime. That's okay. I feel like I did learn a lot. I learned about what those numbers mean in terms of accuracy. I learned about that tier list prompt. I think is brilliant. I think I'm going to use that more. I thought of that last night, but you can get a sense for what those values mean. So yeah, here's the naive model. Here's the performance metrics for that. Yeah, here's Holt Winter's model, performance metric for that. And then profit model, performance metrics for that. So I think that's probably where we're at. LSTM model is next. So let's skip ahead to the bookmark. I think we're probably already at the LSTM model, actually. I think we're probably in the next few pages about to print off the performance metrics. Yeah, so the performance metrics will be printed off here. It will receive sequences of 2016, which will go through 2 layers of LSTM, with the expectation that it will learn the time relationships between the different observations of that week. Then the output of the last LSTM will be the input for a few dense layers that will do the last analysis to extract the final 300 value vector. You can see I am using a different approach compared to earlier examples where there was a time distributed layer on top of which the dense layer was added. The reason for the change is only to show you different architectural options, not because this one is fundamentally better or more adequate for this use case. We have configured similar checkpoints as before, and we can proceed to trigger the training process. All right, so similar checkpoints as before. We're triggering the training process. There we go. Note a few things. We are now truly using y_train for training. In the anomaly detection, when we used neural networks for autoencoders, we were using x_train as opposed to y as the labels as well. This is a true regression use case. LSTM is extremely slow to train. Oh, that's no good. And we are using here as an input a quite long vector with 2016 entries. So it has to unroll 2016 instances of LSTM modules and force data to go through them. We will later train a model for the same purpose with dense layers, and it is much faster. I am using GPUs in Google Colab. I am not. And still each epoch is taking around 25 seconds, and there's 2016 epochs. So I'm American. I'm from the USA, so I can't do that in my head. I can, but I have a calculator right here. So it's going to take this many seconds. So divided by 60, it will take this many minutes. Divided by 60 again. It will take this many. Wait, what? I'm not doing this right. So yeah, so each epoch is going to take 25 seconds. So the number of seconds will be this times 2016. So that's the number of seconds. So to get the number of 60 seconds are in a minute, so we can divide it by 60 to get the number of minutes. There, now I'm doing it right. So we have 840 minutes divided by 60 again, because 60 minutes are in an hour. And it's going to take 14 hours to train. Oh, man. I think that's an accurate number. Okay, well, shoot. Frankly speaking, the training didn't go well. It started improving in the first iterations, but soon it plateaued and did not improve at all after that. It is not a good sign. Probably the architecture is not the right one. That is part of the process. What is wrong with it? Not clear. We may need to test different options to see what changes. Probably we do not have enough data and the model is not able to learn. LSTM models in general require a very large amount of data, and we are using a reasonably small data set. If we plot the training history, it is not clear if it was a good approach or not. Okay, so there we go. There's the training history. And here's the big one. This is the tier list of, so 2, that's F tier. If we run our performance metric for the LSTM model, clearly we did not do a good job. Yeah, F tier by far for all of that. Results are much worse than our simple baseline. If we visualize the results, we get the following. Okay, so very noisy result. Probably, even though we have used LSTM, it has not been able to properly capture the long and short-term differences. And on the other hand, it seems it has learnt quite a good amount of noise from the anomalies, which might be an indicator also that it may be overfitting. While it is true that we are dealing with sequences, we only have one variable, so nothing stops us from using the input vector of length 2016 to feed a standard feed towards dense neural network, so why not give it a try? Since data has already been prepared and we need the same input and output, we do not do any further data manipulation. We can jump directly to define the model we want to train. The following is the model I've used. Okay. It is purely based on dense layers with an expectation that the input vector of 2016 entries will produce an output vector of 3000 entries corresponding to the forecasted values. All right, and it's tradition on this channel to just put these in and see what ChatGPT says, so it gives me a little bit of a break too, so I'm going to do that.
The provided image illustrates a neural network architecture designed to transform an input matrix into an output vector through a series of dense, fully connected layers. Here's a detailed breakdown of the architecture. Architecture breakdown input matrix. The input matrix is of size n times 2016 times 1 n times 2016 times 1 n times 2016 times 1, where n and n is the number of observations, and each observation is a vector of length 2016. Flattening the input, a single input vector, one observation, of size 1 times 20,161 times 20,161 times 2016 is extracted from the input matrix. Dense layers. The input vector is passed through a series of dense layers. First dense layer, 1024 neurons. Second dense layer, 1024 neurons. Third dense layer, 512 neurons. Fourth dense layer, 300 neurons. Output vector. The final output is a vector of size 300 times 1300 times 1300 times 1. Purpose and usage purpose. This architecture is typically used for tasks requiring the transformation of high-dimensional input vectors into a lower-dimensional representation, which could be for purposes like classification, regression, or feature extraction. Input. Each observation is a high-dimensional vector, length 2016, possibly representing time series data, text data, or any other sequential data. Output. The resulting vector of size 300 represents the processed information from the input, suitable for further analysis or direct use in tasks like classification or regression. Summary. This neural network architecture is a straightforward feed-forward neural network with several dense layers, designed to reduce the dimensionality of the input vector while capturing its essential features. The sequence of dense layers enables the model to learn complex relationships in the data and produce a compact representation in the form of a 300-dimensional output vector.
All right, so couldn't have said it any better myself. Still working, so let's. But it looks like it's actually getting pretty far. So we got past the part that takes forever. Now the 17-hour one. Which cell is that? I forget, but it's yeah. So we're making good progress getting through here. I think the 17-hour cell was let's see here. I think it was this one. Yeah, so we do have a cell that presumably will take 17 hours to finish. Let's see where we're at in the book. So we're model.compile, loss equals MSE. Yeah, so this cell, I think this might be the 17-hour one. Oh, no, it's not. So it finished. Now we've got a few warnings here. So could not open a file, but that has nothing to do with the system path. What that has to do with, looks like my kernel was built without NUMA support. I don't know how to do that. Then we've got some, we can't open some CPU libraries. So, yep, they're not installed properly. Yep. So we're skipping that. And then we're passing an input shape to argument to a layer. Yeah, so warnings, they won't prevent it from running at all, but it will prevent accurate results. If you're trying to do a application for something you want to use for production, at least use Google Colab, or maybe some other sort of tool where you can pay for better performance, and you don't have to do all the installations of this stuff yourself, because you just won't get it right. It's too complicated. Okay, while the model seems simpler architecturally speaking, it has a much larger set of weights to train 3.79 million versus 1.73 million in the case of LSTM. It has more than twice the number of weights, so it has more power to learn potentially. Let's see how the training goes. So let's see how the training goes. It looks like I didn't do the training yet. So that's going to be done here. It's going to be the history equals model. So advance the bookmark and get down to that cell. So this cell here. There we go. Looks good. Just giving us information about the data that we're going to load into the training. And we got so we got the same problem that we've had before. This one is easy to overcome. In fact, I can look at a version. So if I just open this in browser, there we go. I actually overcame this in a prior notebook. I forget which one exactly, but I remember how I did that. Okay, so I don't think it was in use case 3. I think it was in use case 2. It might have even been all the way back in use case 1, but the solution was changing something to .keras. So I think we need to use a different search term. Okay, I think it was all the way back in use case 1 where I had to do that. We've also got this second notebook in use case 2, but we've only got 7 hits on .keras, so I think it was back in use case 1. Yeah, so now we've got a lot more hits on that. Yeah, so this is how we fixed that. We changed the file path to and then we also went into the files here, and we can see the change where we did that. I guess I don't see that. Now I did make a commit, so if we go to use case 1, we should see, yeah, so it's not going to show up once it's been committed, but we can see in this commit use case 1 complete. We should have changed the timeline of there should be a timeline change in some of these files. What we might be able to do is view a prior change. All right. Well, I'm confused in that. I mean, we can look at if we go to the terminal and then open a new one, and then go to get just do a get status for a sanity check. And then get log 1 line. So we're here. Yeah. So let's do a get show on this hash. Okay. So we can see we updated the get ignore. Okay, and then we can see we updated the actual Jupyter notebooks, which makes sense. Now we've got another application running. Okay, not sure what's going on with that. Okay, so we updated quite a bit with the Jupyter Notebook. All right, not sure what's going on with that. Huh. Well, you know what? It doesn't matter. So I'm going to get rid of that. Okay, and I just remember what I did, so I'm just going to do it from memory. We go into use case 4. We change the name of this, and we can see an example in use case 1. Yeah, so we can see it's changed to .keras. So we have to do this for the file we're interested in, which is this one here, weights.autoencoder, weights_autoencoder, auto MSE best. Okay, and then we need to modify. Oh nope, this is our example. So we got to do it for the production one. So we got to collapse UC1. There we go. And then the file we're interested in is weights LSTM forecast MSE 2016-300. Yeah, LSTM. There. This is the one we're interested in. So we've got to change this, rename it to .keras. There we go. So it must end in .keras, and then this one I believe we have to change as well. So this is LSTM_best. It's the same file that we see here, but I think it has to be renamed to something else. All right, but let's take it one step at a time. Let's now that we've got that changed, we're gonna get rid of this. Do a clear. Open Jupyter Notebook again. Open this in a browser. And go to UC4 to this. Okay, and then we're just going to go all the way down. It's going to take a while for it to run, but we'll do some reading in the meantime. Okay, and before I go on, change this to Keras now that it's been renamed. And hopefully this can run correctly, and then we'll address this cell when everything is ready. The first thing you will notice is that the training goes really fast. It takes less than 1 second per epoch, and it converges quite smoothly as the training grows. If we visualize the training process, it looks like this. There we go. Both train and validation curve improve consistently, and the validation curve is also consistently below the training one, which means the model is not overfitting. It is generalizing well, likely due to the dropout regularization we are using. Let's remember, dropout makes it harder for the neural network to train, as some percentage of the perceptrons are disabled randomly in training. It makes it more resilient to biases and specific output variables as it forces it to learn better to capture the internal patterns on the input data. Ultimately, it generalizes better when exposed to unseen data. The performance benchmark shows a much better result compared to the LSTM, but it is not on par yet with the other models, and it is worse than the baseline model. So here's the results. F tier, the clear F tier for all the results. This might be a D tier, actually. I don't remember what the tier list was. I think it cut off at 50 between a tier, so that might be a D tier result rather than an F tier result. I wish I could go back and find that easily. And you know what? I think I can if I search for tier, T-I-E-R. Yep. So, oops. And it's now the result of clicking in that same area somehow is different. And instead, I clicked on my bookmark. Okay, so it looks like it flipped the menu over for some reason. So here's the tier. D tier is cut off at 50. So congratulations, it made it into the D tier. We'll see what mine does, probably an F tier. However, some fine-tuning could lead to better results. If we visualize the predicted versus actual, it shows how the model has captured quite well the pattern and knows that given the day of the data predicted, the peak is low in the seasonal period. If we do a zoom, we can see it is anticipating quite well the metric changes, but without the anomalies. Note that the anomalies are contributing to the loss as well. All right. Now let's try, okay, so we're moving on to another model here. So I'll advance the bookmark and check back in. It's still running, but we're moving down to this next section, dense model, I think. Oh no, we're actually moving all the way down to the auto ARIMA model. Okay, so this is probably still, this part takes like 5 minutes. So that's okay. We can keep reading. It's all kind of going over my head anyway. Let's try now another quite popular model for forecasting, ARIMA. Another auto-regressive model which does not look like seasonality. ARIMA, I'll call it that, requires a certain selection of input parameters. We are going to apply AutoML techniques to let the system figure out what those combinations of parameters are for us. Therefore, it will run ARIMA multiple times to find the best combination. Again, brute force is our friend, always in machine learning. The more power, the better. We can now generate the forecast for the next 300 data points. The result is a data frame with new observations predicted in the future with respect to the data we provided for training. Let's evaluate the performance of this algorithm against our previous benchmarks. All right, so now, really, really, really bad. Breaking the tier list. You have to create a new tier beyond the F tier for that. Not a good result, definitely. If we visualize the data, it is very clear that the model has not learned properly the input variable. Now let's be a bit more creative and see what happens. Earlier, we have seen that the LSTM model did not do a good job. Maybe the vector we are providing is too long and it is not able to learn the seasonality in such a long sequence. However, if we introduce a shorter vector, let's say 1 day or a few hours, it will not have any possible way to learn the weekly seasonality. It should see at least 1 week worth of data in the input sequence to understand how the new 300 points need to be generated. However, we can manipulate the data in multiple ways, and it is our responsibility to find the most convenient way to present the data to a model so it can learn. It is the feature engineering process. We have also mentioned that one of the key advantages of neural networks is that somehow they automatically do the feature engineering process, and that is true to some extent. There are certain features that it is very unlikely that can be learned automatically or not in a certain training time frame or specific network architecture. For that reason, we can always help the neural network with our domain expertise about what may be relevant. So what is the proposal? The proposal is to feed a neural network, in this case LSTM based, with two input variables. One is the short-term history of the metric, let's say the last 1 day of data. That would give the network the ability to learn how the last day impacts the new data to be generated. Now we add a second input variable, which is a summary of the last 7 days, a sort of rolling average resampled in 288 points, which are a number of points exposed in the first metric. Therefore, we have two input metrics. One provides information of the last day, the other one provides information from the last week, but in a summarized way. This gives the model a perspective on how it is supposed to behave given the current data point and the long and short-term history. It seems a bit convoluted, but it is a hypothesis worth trying, as both input variables seem useful and relevant to facilitate the training of the model. Now our model will not get a long 2016 vector, but a smaller matrix of 2 by 288. The following code snippet is the loop to extract the new training data, part of which includes computing such as rolling sampled windows from the past 7 days. We will use exactly the same model we used earlier for LSTM. The only difference will be the size of the input vector, but the model layers will be the same, as well as the number of weights. Visually represented would be as follows. So that's what I like to do, is plug those in. Okay, and while it's waiting to read it back, we'll see how far we are. Looks good. Okay, I forget what I did there.
The provided image illustrates a neural network architecture involving LSTM, long short-term memory, layers followed by dense, fully connected layers. Here's a detailed breakdown of the architecture. Architecture breakdown input matrix. The input matrix is of size n times 288 times 2n times 288 times 2n times 288 times 2, where n and n is the number of observations, and each observation is a matrix of size 288 times 2288 times 2288 times 2. LSTM layers. The input matrix is fed into a stack of LSTM layers with 256 units each. The LSTM layers process the input sequentially, and only the last LSTM module returns the output. Output from LSTM. The output from the last LSTM layer is a sequence of 256 features, resulting in a vector of size 1 times 2561 times 2561 times 256. Flattening. The output sequence from the LSTM layer is flattened into a vector of size 256. Dense layers. The flattened output is passed through a series of dense layers. First dense layer, 1024 neurons. Second dense layer, 512 neurons. Third dense layer, 300 neurons. Output vector. The final output is a vector of size 300 times 1300 times 1300 times 1. Purpose and usage purpose. This architecture is designed to process sequential data, like time series or text, using LSTM layers to capture temporal dependencies, followed by dense layers to transform the LSTM sequence output into a fixed size output vector. Input. Each observation is a matrix of size 288 times 2288 times 2288 times 2, possibly representing two features over 288 time steps. Output. The resulting vector of size 300 represents the processed information from the input, suitable for further analysis or direct use in tasks like classification or regression. Summary. This neural network architecture leverages the capabilities of LSTM layers to handle sequential data, capturing temporal dependencies and patterns in the input matrix. The subsequent dense layers further process the LSTM output to produce a compact and meaningful representation in the form of a 300-dimensional output vector. This structure is commonly used in tasks that require understanding and transforming sequential data into a lower-dimensional representation.
All right, so that looks good. So I remember I was able to deal with this before, so I forget how. Let's try loading this with the Keras. Okay. So it's not a zip file. I think this might have to be dot. H5. Right. No, this one has to end in Keras. Okay, and this one I think has to end in like that. But the file is, yeah, the file is not found. So how is it in the other one? So did I just... Oh, I have two different files. What? Yeah, so it looks like I have two copies of each file. But here I only have... Oh, I have... No, I only have one copy of each file in best dot... in .hdf5, which we know does not work. So let's go to my GitHub and see what the original looked like. So one of my repos is from the, yeah. So we'll go to the original repo, and then we'll look at what the files were when they were unmodified. So we had auto and we had best. So I feel like I generated a file in the code somewhere. So let's take a look at the weights dot yeah, so we can see this file path here. Or what? Where is that being fed in? And I did a lot of craftiness there that I don't know if I can. So we made a checkpoint out of the file, and that checkpoint has to be a Keras file. Yeah, so checkpoint equals that. That's a Keras file. So we should have done something pretty similar. the next thing we did is load awaits. Okay, so yeah, here's the checkpoint file, and then yeah, so it does need to be like this. Right, and we redefine the so this does need to be the waits for use case 4, and then we redefined the file path. Yeah, so we did a lot of really crafty things here. We defined the file path here. Then we ran it and created the checkpoint. And I think the checkpoint is probably this file. So now we redefined the file path. So we did not redefine the file path yet. So let's do that. Okay, and then we need to obviously put in the correct file. But the thing is that file has to be generated, I think. And I don't think we generated it. So checkpoint equals that, callbacks underscore list. So this should generate that file. Run it one more time here. Yeah, so that went successfully, so it should generate that file. But I don't see it. Oh, you know what? I think it's because right. So okay, I think that's what's going on. So yeah, so here this is, we can ignore this because that's successful. So basically need to do kind of a lot here. So we have to, so this is what we do. We do a file path that join. So we did that there, and then the model that load waits. Okay, so yeah, I think we don't want to load the weights. We want to get the weights ourselves. So this is, you can cheat and you can use the weights that already exist. But we don't want to do that. We want to generate our own weights file. Yeah, so let's just get this for a sanity check, like there, so that it matches that. Yeah, and here's the code where if we want, we can load our own weights file. Okay, so this code should run now. We're in use case 4. Looks like we already ran it by accident, but let's run it again. Okay, and now we should see. Yeah, so we got the Keras in there, but we don't have the weights that one there yet. That's okay, because we need to. We're gonna create that. So okay, so moving on to this cell. Allocation exceeds 10% of free system memory. That's not good. But it's just a warning, so it should be fine. Now I think this is probably the 17-hour one. Unfortunately, this is where I think we have to save the weights in the different file name. Okay, so we can save it as .keras. Yeah, so we have to change this to Keras. Looks good. Looks good. All right, all of that looks good. So, all right, let's do some reading. Now, we might have to, unfortunately, skip doing this locally. It's really meant to be done on Google Colab, so I think I don't have the firepower for it. We can see I'm out of memory. It's going to use GPU, it's going to use CPU, it's going to use memory. So just because you have a nice GPU on there doesn't mean you'll be able to run it as well as somewhere else, especially Google Colab, which is designed to be used for these sorts of applications. So yeah, let's continue reading. When we run the training, I will skip the capture this time. You can look at it in the notebook. We can immediately see the training is much faster than earlier because now the unroll process is almost 10 times smaller, from 2016 to 288. It is true there are other dimensions. It is true there are other dimensions are 2 versus 1. And I think this is meant to be a THEIR. That's just a confusing sentence to read. But that does not impact the unroll time. The results are about 22% better. Before we had a MSE around 1.75, and now we have around 1.45, which is still very, very bad. The benchmark is substantially better than the previous LSTM, but still far from other methods we have used in this use case. More work is required to improve the LSTM approach. All right, so we can see F tier still. Very bad results. LSTM is producing a very noisy prediction of the next 24 hours of subscribers. I'm hoping where the author is going with this is by the end of all this stuff with LSTM, it's the most accurate of all of them, and showing that it's worth it to go through all this rigmarole to get there. But we will see. So far, every improvement has stayed solidly in that F tier of accuracy. Okay, so now, the kernel died, so... Okay, so we're kind of off the rails now. I feel like the kernel dying is a big deal. It's just kind of what I think about that. So the kernel died, it restarted, and now we're running cell 1. I guess I can try restarting and clearing all output and doing it again, but I think the kernel's just going to die again. Yeah, it's meant to be run in a Google Colab, so I just don't have the kind of firepower that I need to run this locally. Okay, but we'll give it one more try, and then in the meantime, keep reading. All the way down to the score. Okay, so, but we can try one final thing. What if we combine the long and short-term data in a single vector and feed a dense network like we did before? Maybe this helps improve as well. Ultimately, we are giving similar information, but in a more compact way, so the dimensionality reduction will help improve the training process, as we have discussed in the book. Let's concatenate the two vectors from the previous example into one. This means our training data now looks like this. Instead of a 2 by 288 matrix per observation, now we have one vector of 1 by 576, which will be the input for our dense feed-forward neural network. We will use the same neural network as earlier, as we want to evaluate to which extent this change improves or not the result. Okay, there we go. As a reminder, the following is the neural network we will use. Looks good to me. With the change in the length of the input vectors, the number of parameters in the network has reduced substantially to now only 2.3 million. So, okay, we've got it reduced to 2.3 million. Looks good. The training process is, as in the previous case, very fast, and immediately we can see the results are encouraging. Whoa, look at that. With a test score for our test data of 3%, close to 4%, versus 0. Was around 7% in our previous use case. Now this is a different score. I don't think this is the this is the MAE and the MAPE. That is around 44% improvement with a much smaller set of weights to train. The performance benchmark also provides quite good results. Wait, what? No, it doesn't. Oh, I think this might be a 0. So yeah, if it's 0.34, that changes it out of the F tier. But yeah, it's worse. While still worse than the baseline, Holt, Winters, and Profit, it's the best result of all neural network-based approaches so far. So that's one thing to know. Holt, Winters, and Profit are not neural network-based approaches. LSTM is a neural network. So perhaps the advantage you get of this is you can just keep brute forcing it until you can outperform those other ones. Whereas with those other ones, since they're not neural networks, you can't take that approach quite the same way. But that's just an assumption I have. The visual representation also shows that the model seems to capture quite well the variations in the input metric while ignoring the anomalies. All right. Yeah, so now this is what we're trying to do, is get that graph to look the same, the predicted to look very similar to the actual. And now we're at the takeaways. So let's check back in at the notebook. It was really meant to run in Google Colab, so it's no surprise that the kernel is dying and all sorts of other crazy things are happening. We're getting warnings after warnings. Pink is not a good color to see in Jupyter, and I'm seeing a lot of it. So okay, so let's finish this up with the takeaways, and then if the kernel dies again, we'll just move on from it. I can't get it to work. Should be doing it in Google Colab anyway. Takeaways. We have reviewed a number of algorithms and methods to forecast the value of a metric. These are just a sample of a broader spectrum of techniques. The intent was to show again that there is no one-size-fits-all approach, and different algorithms may or may not work for your data. However, even more important is the learning that the key is on the experimentation and trying different approaches. In machine learning, pretty much everything is trial and error. Whether we do that manually or with automated techniques such as AutoML is a choice. Keep in mind also that using LSTM requires a large amount of data, probably much more than what we had in this case. Training takes much longer compared to other architectures such as forward feed dense networks. In metric forecasting, seasonality is a key component to detect and understand and manage it accordingly. We would have had better results very likely had we extracted the seasonal components before training any forecasting model and then brought it back afterwards. Similarly, we should have detected the outliers first, as we did previously, and removed them before forecasting. They are also to a certain degree influencing the results. Intuition will always play an important role. The intuition of what data may be relevant for your use case or what feature engineering to perform. You will build that intuition over time. Last but not least, the key is on the data. You have seen how by doing a more intelligent management of the data and presenting both the short and long-term data in a vector, we have obtained a much better result with a much simpler model. This confirms that the key is not in the model, it is in the data. Further work. It may always be interesting to learn and evaluate other algorithms, but one interesting angle to explore as well would be to add multiple variables. What if the number of subscribers is a function of other variables, not just the number of subscribers itself? Evaluating some of these algorithms with more than one input variable may drive new interesting results. Likewise, we have used some neural network architectures with some pretty much randomly chosen number of layers and nodes per layer. Evaluating an AutoML approach to validate a wider range of options and find the optimal could be a recommended next step. All right, so on to use case 5. Is the cabling in my network correct? So get rid of that. I do want to check back into the highlights, because now that we are learning about different kinds of algorithms, I want to go back and remember the algorithm that was used to win competitions. So I remember it was not a neural network algorithm. So I think if I search for Kaggle, so Bruce says one of the most powerful and flexible links preferred choice. Yeah, so this deserves a highlight. I want to be able to go back and remember this XGBoost if I ever in the future do a competition. Okay, so there we go. Let's see here. So, yep, we're gonna check in on my my not good enough architecture here. So we're doing a Holt Winters algorithm on this data frame. Which is taking a while, and then we have no frequency information, so we're using an inferred frequency, which will ruin things. All right, and that's going to take a while. So I kind of want to just wait it out, because I think that's important. We can't really, I don't want to move on to use case 5. I want that to start in its own video. So yeah, we just gotta wait it out a bit and see what's happening. If the kernel crashes, that'll be it for the video, but hopefully that doesn't happen. All right, and let's take a look in the meantime at this file here. Okay, back at the use case 1, because this is the problem, is interacting with these files. File path equals that, and then I guess this is just if you want to use the existing, if you want to generate your own. Oh, this is to save it. Oh, but it's just join method for loading. Is that why? Okay, so the kernel died. It just can't do it. It's meant to be done in Google Colab, so my local hardware isn't working, and we weren't able to get the NVIDIA monitoring tool to open to see what's happening. Anyway, we can see we got a lot of warnings. I didn't install some basic things correctly, so that could be causing it as well. But that's it. That's okay. We don't have to get every little thing to work. It's challenging, so yeah, that's it for this video. Thanks for watching. See you in the next one.